Now the simplest polynomial is a first degree polynomial, which is simply just a straight line, either from bottom to top or from top to bottom like this. And the formula for this is ax plus b. Now this is called a polynomial of first degree because invisibly there is a x to the power of 1. So, and this is the highest power, the highest exponent, and so it's a polynomial of first degree. The second would be this. We all know that is a parabola, and the equation for this is ax squared plus bx plus c. Now the question is, why is it sometimes like this and like this, or like this and like this? It depends on the coefficient which stands in front of the x with the highest exponent. So in this case, this is the a here, and if that a is positive, then we have this, and if that a is negative, we have this. For example, if we have a line which is y equals 3x plus 5, then it's positive, it's like this. Or if it's minus 3x plus 5, then it's like this. The same here. If a is positive, we have this parabola, and if a is negative, we have this parabola, which is downwards open downwards. So the next would be a polynomial, a third degree polynomial. Either it looks like an n or like a reverse n, like this. And the equation is ax cubed plus bx squared plus cx plus d. And again, it depends on the a, on the coefficient in front of the highest exponent, whether it is so or so. So if a is negative, if a is positive, it looks like this. If a is negative, it looks like this. Noteworthy is that if we compare these two, the third degree and first degree, in both cases we see it goes from bottom to top, from bottom left to top right, and also here from bottom to top. It goes up, even though there is some region here where it goes down, but globally it goes from top to bottom, from bottom to top. Also like here, the straight line goes here from top to bottom, and also here from top to bottom. Globally it goes down, even though there is some region where it goes up. So the next is a fourth degree polynomial, which is ax to the fourth plus bx cubed plus cx squared plus dx plus e. And that looks like a w, or it looks like an m. Now again, noteworthy is, if we compare these two, the parabola and this, we see in this parabola both arms, left and right, they go up. This is the same here also. And in this parabola, both arms go down, and here the same, both arms go down. Again, it depends on the a. If that is positive, it looks like this, just like with the parabola. And if a is negative, it looks like an m, like this parabola. Next, we look at the y-intercepts. The y-intercepts are where the graph of the function intersect the y-axis, which is, in the case of the straight line, here and here. Or in the parabola, it's here and here. Or here, 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 here. So the y-intercept we calculate the y-intercept simply by calculating f of 0. That means if we have the polynomial, we set in a 0 for every x, and then we calculate What we see then is that this gets 0, and only the c remains. Similar here with the straight line. This gets 0 and only the b remains. Here only the d remains, and here only the e remains. And this last here is always the constant value. That always tells us where the y-intercept is. For example, if we have a polynomial that looks like this, minus 3x squared plus 7x plus 2, we immediately know that the y-intercept is at plus 2, because these two, they will get 0 when we set in a 0 for the x and only the 2 remains. So we do not really have to calculate the y-intercept, we immediately see it. The next thing are the roots, the zeros of the functions, which is the intersection with the x-axis, that is here and here. The linear functions, they will always intersect exactly once with the x-axis, because they are either going up or down, and sooner or later they must intersect the x-axis once. And then the parabolas, in this case, they are intersecting, they both intersect the x-axis twice, but it can also look a little bit different. I will show this on the small paper. This is the x-axis, and of course it can look like this. Then we have a parabola that is intersecting twice, but if we move it up a little bit, it looks like this, and we have only one root. And if we move it even further up, then it looks like this, and we have 0 roots. So these 2 roots, this is just the maximum number of roots. It's not always 2 roots that a parabola has. So the third-degree polynomial in this case has 3 roots, and here also 3 roots. But again, it doesn't have to be 3 roots. This is just the maximum number of roots. We see that here again. So it can look like this. Then we have 3 roots, 1, 2, 3. But if we move it up, it has only 1, 2. If we move it even further up, it has only 1 root. Third-degree polynomial can never have 0 roots. That's impossible, because it always goes infinitely down and infinitely up, and so sooner or later it must cross the line. So the maximum amount of roots of a third-degree polynomial is 3. Roots here we have 1, 2, 3, 4. 4 times the x-axis is intersected. And here in this case only 2, because I have drawn it in this way. It was just randomly. But again, as we see here, we have this is a maximum number of roots, 4. It can be less. I show it again here. 4 is like this when it crosses 4 times. But it can look like this, then it crosses only 3 times. It can look like this, also 3 times, but it looks differently. But there are many other possibilities. It can look like this, then it crosses only twice. It can look like this, it crosses only once. And finally it can look like this. Then we have 0 roots, no roots at all. So the maximum amount of roots that a fourth-degree polynomial has is 4. So, and that makes clear that the maximum amount of roots is equal to the degree of the function. If the degree of the function is 3, like this, the highest exponent is 3, then the maximum amount of roots are also 3. We calculate roots by setting f of x equal to 0, and then whatever equation we have, we solve for x. The next thing I want to look at is the extrema, which can be either maximum points or minimum points. So a straight line, has no extrema, no maximum points, no minimum points, but the parabola here has a minimum point and here a maximum point. So the parabola, the second degree polynomial, has one extremum, and the third degree polynomial, as we see, has two extrema, one maximum, one minimum, and here also one maximum, one minimum. But it can also be less. We can have a look at this. A third degree polynomial can look like this. Of course, then we have two extrema. It can look like this, still two extrema, but as you see, the extrema are now closer together. And that leads us to a point where the two extrema have fused, so to say, to one point. That is just a stationary point, a saddle point. And it can go even further, that we don't even have a saddle point, just an ordinary inflection point here. So in these two cases, we have two extrema, and in these two cases, we have zero extrema. It is not possible for a third degree polynomial to have one extremum. That's not possible, either 2 or 0. Now the fourth degree polynomial has 1, 2, 3 extrema in this case, and 1, 2, 3 extrema in this case. But again, here, this is just the maximum amount of extrema that we can have. It can look like this. Then we have 1, 2, 3. But just as before, for example, these two can fuse together. Then it's only a saddle point, which looks like this. So this minimum point is just this one. But these two have fused to the saddle point. That means now we have only one extremum, only one, because this is not an extremum. We have 3 extrema or 1 extremum. We calculate the extrema by setting the derivative f prime of x equal to 0, and then we solve for x. And the last thing I'm talking about are the inflection points. So before I talk about the inflection points, I want to make clear what inflection points are, because many students have problems to understand what that is. If we have such a function, here's the inflection point. Why is that so? The inflection point separates a right-hand band from a left-hand band. Before the inflection point, we have a curve, a bend, a right-handed band. And then comes the inflection point, and after it, we have a left-hand band. So that's an inflection point. So obviously, a straight line cannot have an inflection point because it has not even a bend. Then the parabola also has no inflection point because it is only one bend. It is, in this case, it is just a left-hand band, or in this case, it's just a right-hand band, but there are no two bands. The first time we have two bands are the polynomials of third degree. And where is that? Now this inflection points randomly, in this case, is roughly equal to the root. And here, it's roughly here. It separates, this inflection point separates this right hand bend from this left hand bend, and here vice versa, left hand bend from right hand bend. And the polynomial of fourth degree has two inflection points, here and here, or here and here. We calculate inflection points by setting f double prime of x equal to 0, and then we solve for x. So I hope you have understood a little bit, and hope to see you next time.